In this video, we're going to see a different algorithm for the fast Fourier transform, an algorithm that's not based on recursion. So recursion is advantageous because it gives a natural splitting of the problem into partial problems. It prevents a lot of bookkeeping, and it is a very concise formulation of the algorithm. And as a bonus, with the recursive algorithm, the problems that have been slimmed down to small problems may fit into the cache of a computer, and hence recursive algorithms can be very cache-friendly. The downside is that even though there may be parallelism pointed to by the recursion, the way we travel through the computational tree is sequential, and that's not exactly the order in which we can exploit the parallelism. So we're going to look at the Fourier transform in matrix terms, and having the matrix Fn, the Fourier matrix, assume that we can decompose it into a product of matrices A0 to AR. Then if we have that, we can perform the Fourier transform by multiplying each time a matrix AI with a vector x. And here we have a matrix which occurs during the Fourier transform in matrix notation, which is called omega. And omega in this case is a n/2 by n/2 matrix, which contains all the weights, all the powers of omega that we need in our algorithm. So it's very useful to have this omega matrix to formulate our algorithm in terms of matrices and vectors. So the Fourier transform then is a multiplication of the matrix Fn with the vector x, and we can write it as three different matrices. On the right, you see a short notation for picking out first the even components of the vector x, so starting at 0 with a stride of 2, so 0, 2, 4, 6, etc., at most up to n-1. And then below that in the vector, we have the other n/2 odd components of the vector x. So that's a way of writing down the sorting that we do of the even and odd components of the vector x. And then we multiply each part with a Fourier transform of half the size. That's what we did in the recursive algorithm. So in the middle, you see a diagonal matrix with blocks on the diagonal, and each block is a Fourier matrix itself, but of half the size. And then to the left, you see a matrix which consists of 4 blocks. On the left, you have identity blocks, and on the right, you have this diagonal matrix omega, once with a plus and once with a minus sign. And now if you think about it, multiplying this matrix with the vector, with the Fourier matrices in between, exactly picks out the addition and the subtraction that we have in our recursive algorithm. So this is a different way of writing the Fourier transform of a vector x. And now we want to introduce some more notations to make, in the end, to get a formula which is as concise as possible and which expresses the recursive algorithm. And for that we need a permutation matrix, so a matrix with in every row a single 1 and in every column a single 1 as well. And this permutation matrix contains, first of all, the even rows of the identity matrix, and then the odd rows. So what it really does is, if you multiply this matrix, which is called the even-odd sort matrix, Sn for short, if you multiply it with a vector, it picks out the even components first and then the odd components. Another useful notation for matrices is the multiplication of two matrices, but not in the conventional linear algebra sense, but in the Kronecker or tensor product sense. And what it does is, if I multiply a matrix A, Kronecker, by B, then you create a much bigger matrix which contains copies of B, but scaled by the elements of A. So, as an example, if we have a matrix A, which is a 2 by 2 matrix, 0, 1, 2, 4, and a matrix B, which is a 2 by 3 matrix, with the first row 1, 0, 2, the second row 0, 1, 0, then A Kronecker B is just a matrix which contains in the left upper corner 0, right upper corner a B, and the left bottom corner 2B, and then 4B. And written out, you get the matrix that we see down. So that's what the Kronecker matrix product does. So I have a question to you. What is the matrix I4 times A? Well, I4 is the 4 by 4 identity matrix, and A is the matrix 0, 1, 2, 4 that we just saw. So, since I4 is a 4 by 4 matrix with 1s on the diagonal and 0s elsewhere, then we get 4 copies of this matrix A on the main diagonal. I haven't shown all the 0s in the matrix. I represented them by dots, but you see the matrix 0, 1, 2, 4 copied 4 times on the main diagonal. And that's actually what we will use the Kronecker product mostly for. Now, the Kronecker product has a number of useful properties. First of all, you don't need to write brackets. Associativity. If I do a Kronecker product of A times B and then times C, it's the same as first multiplying B and C in the Kronecker sense and then multiplying by A. Also, we can mix the regular product with the Kronecker product in the following fashion. If I have the Kronecker product of A and B, and also the Kronecker product of C and D, I multiply them in the regular fashion. It's the same as multiplying A and C regularly, B and D regularly, and then multiplying those products in the Kronecker sense. There's one provision that has to be fulfilled. AC must be well defined, so the number of columns of A must be the same as the number of rows of C, and similarly for BD. We are interested in using the Kronecker product also for identity matrices. So if I have m copies of an n by n identity matrix on the main diagonal, then of course I have m times n ones on the main diagonal. So that is another property. And another property that we would like to have, but that doesn't exist, is commutativity. Similar to the regular matrix product, there's no commutativity. Here we don't have that as well. Okay, so how do we use the Kronecker product? The main way we do that is by writing, for example, I2 Kronecker Fn over 2 is this block diagonal matrix that we already saw with smaller Fourier matrices on the main diagonal. And we will use this notation to derive a non-recursive fast Fourier transform. Okay, so this is the picture. This is how my daughter, when she was 8 years old, pictured me with glasses, pointing at the screen and explaining what a butterfly is. Now, I will explain to you what a butterfly is, not the one that you see in nature, not the one that you can see outside in our botanical garden. No, we have a butterfly in the Fourier matrix. And what happens deep inside the algorithm, we have that we combine two values, xj and xj plus n over 2 at a distance n over 2. We combine them by multiplying the xj n over 2, xj plus n over 2, multiplying it by an omega, and then adding and subtracting this. So we have two inputs, xj and xj plus n over 2, and two outputs, and we denote them by a prime. So xj prime and xj plus n over 2 prime. And if you depict them in the way that I do, you get a butterfly. And that's why we call this operation a butterfly operation. And when we have a butterfly operation, we also have a butterfly matrix. So the butterfly matrix is just the matrix that I have shown you before. Bn is just 4 blocks, 2 identity matrices, and the omega n over 2, and also with the minus sign. So as an example, if we look at B4, then the omega that is there is omega 2, which contains all the powers of omega 4. So omega 4, if you compute it, it's just minus I, the complex I. So we have B4, you recognize on the left 2 identity matrices on top of each other. And on the right, you recognize the diagonal matrix with powers of minus I on the diagonal. Now, we have minus I to the power 0 equals 1, and minus I to the power 1 equals minus I. So this explains B4. The nice thing about a butterfly matrix is that it is a sparse matrix. It has lots of zeros, and out of the n squared elements, only 2n are non-zero, because every row has a non-zero from the identity matrix and one from the diagonal matrix omega or minus omega. So what did we do? We gave names, we used matrix notation, and that way we could write the operation Fn times x, multiplying a Fourier matrix by x, as a butterfly matrix on the left, Bn, 2 copies of the smaller Fourier matrix in the middle, and then we have Sn times x. So because this is true for every x, for every vector, the matrices must be the same. And that gives a formula which, if you get carried away, you could put on your t-shirt. The formula is Fn equals Bn times I2 Kronecker Fn over 2 times Sn. So this is our recursive formula, and we can use it to derive a non-recursive algorithm. So how do we do that? We already saw a way of making the Fourier matrix smaller. So let's look at what do we do with this factor I2 times Fn over 2, which is in the middle of our t-shirt formula. So what we can do is I2 we can write as the product of 3 matrices I2. They are just identity matrices. I can multiply as many as I want. And then the Fn over 2, there I can apply this recursive t-shirt formula again, but then with n replaced by n over 2. And then we use this mixed products property that we just showed for the Kronecker product, and that means that we can Kronecker multiply every factor I2, and we have 3 of them, with the factors that come from the t-shirt formula. And that gives us, using the fact, for example, in the middle, we have I2 times Fn over 4. I2 times I2 is just I4. So we have written the formula slightly differently. And what you see in the middle, now we are down to Fourier matrices of size n over 4. So this gives us a way to reduce the size of the Fourier matrix, but we get some garbage, not really garbage, to the left and to the right. So, like you can burn a candle at both ends, we are burning here this formula, the Fourier matrix Fn, which is I1 times Fn, and we get each time on the right we get a sort matrix, a permutation matrix. On the left we get a butterfly matrix, or a number of copies of butterfly matrix. And then when do we stop? Well, when we reach the middle and there's nothing in the middle. And when does that happen? When we got down to In times Fn over n. Now n over n is 1, and F1 is the Fourier matrix of size 1, which is just the identity matrix. So we end with In, the n by n identity matrix in the middle. But that doesn't do anything, so we can remove it. And as a result, we get a formulation of the algorithm, a decomposition of the algorithm, which was formulated by Cooley and Tukey in 1965, and that's really the formulation that made the Fourier transform famous and used everywhere. So we have two parts. On the top you see all the butterfly matrices, like from right to left, In over 2 times B2, In over 4 times B4, etc. And we end with I1 times Bn. And then there's also a permutation matrix Rn, which collects all the sort matrices. And you see we have from the right I1 times Sn, and then I2 times Sn over 2, all the sorting. And that goes into a matrix which we call Rn. It is a permutation matrix because it's the product of permutation matrices. And it is called, for some reason, the bit reversal permutation matrix. And then, using this theorem, we can define an algorithm which is a non-recursive algorithm because it doesn't call itself. And what's in the algorithm? Well, you start with k equals 2. You perform n over 2 copies of the butterfly matrix B2, multiplying this with x. And then each time you run through the main loop, you multiply k by 2 because you're doing bigger butterfly matrices, but fewer copies of them. And inside this, you do, as we saw before, you multiply the xj with a component of x. You multiply, you add and you subtract a value, which is this omega times an x component, which we call tau. We've seen it before. And you get the new values of x. And you do that for all the butterflies, for all the copies that you have to do, until k reaches n. So this is a concise formulation of the non-recursive algorithm. Okay, let's summarize. So we have a different version of the Fourier transform now. It is non-recursive. And we call this the Cooley-Tukey decimation in time algorithm. And it starts with a bit reversal, and then it does all the butterflies. Now the number of flops of the recursive algorithm was 5n log n. And this, if you do the calculations, is exactly the same. An advantage of this formulation is that it is amenable to parallelization. And that's what we will see in the next video. A question to you. You may have asked, why is this permutation matrix Rn called the bit reversal permutation? So, first of all, I would like you to compute R8, which is a product of 3 factors. each involving sort matrices S8, S4, and S2. And then, once you've computed that, you should multiply it with a special vector x, namely the vector x which is 0, 1, 2, 3 up to 7. This will give you some insight. And maybe you can answer then the question, why is this matrix called the bit reversal matrix?